Okay, we'll start with the measuring instrument part. So we'll start with the vernier scale. Now you know that in our measuring instrument, we can question with 4 instruments mainly. This one is going to be our vernier scale, and the other one is going to be our micrometer scale gauge. The third one is going to be the sperometer, and finally we'll be having the traveling microscope. So if I write them, vernier scale, sperometer, the micrometer screw gauge, and my traveling microscope. So if you look at the recent time, there has been less questions related to the measuring instrument. You'll be getting a mostly a structure. And the last one which was questioned was the traveling microscope in 2018. So we are having some option from them. So let's have an idea about the vernier scale first of all. Okay. So if I start with the vernier scale, we'll be having a main scale in the instrument and a vernier scale. We'll be having a main scale and a vernier scale. Now, first of all, let's get an idea why we are actually using these instruments. If you look at the ruler, we are able to get a minimum measurement of 1 millimeter. We can't go below it. So in order to have an accuracy, to obtain some small readings, we used to obtain these instruments. So under this case, the vernier scale. So we'll be having a main scale and a vernier scale. In the initial case, we must check for the zero errors. Okay, we must check for the zero errors. And then most of the instrument, the least count will be given. If it isn't given, we have to find it. So let's see the steps in that. So first of all, we must make sure that the main scale 0 mark and the vernier scale 0 mark used to coincide, which means there is no zero error in the instrument. There is no zero error in the instrument. Then this vernier scale is much more smaller compared to the main scale. Then there will be some small divisions in the vernier scale as well as in the main scale. So somewhere at a distance, both the main scale and the vernier scale used to coincide. Apart from the zero marks, somewhere around the main scale and the vernier scale used to coincide. So, generally in questions, it will be 9 and 10. The 9 division in the main scale, 10 division in the vernier scale. Or else they can adjust that. So let's say if n division coincide in the vernier scale and n minus 1 division in the main scale coincide each other, how are you going to find the least count? First of all, so let's say if it is an ordinary ruler, there will be a gap of 1 millimeter. There will be a gap of 1 millimeter between every mark in the main scale. So first of all, let's find this measurement. from 0 to n minus 1. Now we are knowing that there is a 1 millimeter gap between every divisions. So like that we are having n minus 1 divisions. So the length has to be n minus 1 millimeters. If I had 9 millimeters, whatever mark into the least value of n minus 1 into 1 millimeter will be the measurement along here. Will be the measurement along this point. And if you look at the length in this section, there are n divisions, but we must understand we don't have 1 millimeter divisions here. If it's so, every division used to coincide, right? So there will be a different separations between the segment. So let's say the distance between the segment is x. The distance between the segment is x. We are having n number of divisions along here. So this length has to be n into x. If we compare with this, 1 millimeter divisions, we had n minus 1 division coinciding at this point. So this length has to be n minus 1 into 1 millimeter. 1 millimeter was the division between two segments. So the length between two segments. And if you look at here, we are having x between two divisions, and the n division used to coincide. So it's going to be n times of x. Now, what can you say about these two lengths? What can you say about these two lengths? They are the same. So we can equate this value with this, which means n into x is equal to n minus 1 into 1 millimeter. I'm writing this one, there's a reason behind this. So from here, we are able to derive an expression for x, which is n minus 1 over n into 1 millimeter. Now, this is going to be the value of x, which means the smallest division in the vernier scale is going to be n minus 1 over n into 1 millimeter. So how we are going to find the least count? Now the least count is going to be the smallest value which you are able to measure from this instrument. So if you compare both these divisions from the 0 mark, we are having a 1 millimeter gap between these two, okay? That's a 1 millimeter gap. And if you compare the vernier division, there's an x millimeter gap. That's going to be somewhere around here, x millimeters. So if you understand, between these two divisions, there's a small gap. There's a small gap. So this is going to be the least value you are able to measure, and it's going to be my least count. Again, if I repeat it, when I consider the main scale, we were having 1 millimeter gap, and along here, we were having x millimeter gap. So the difference among them, there's a small distance. So this will be my least count. So in order to obtain an expression 1 millimeter minus x will be my least count. Okay. So you can see that x is equal to n minus 1 divided by n into 1 millimeter. When I substitute onto here, 1 millimeter minus n minus 1 over n into 1 millimeter will be my least count. So if I open my brackets, we'll be having 1 millimeter common n minus n plus 1 over n. It is equal to 1 millimeter into 1 over n. So we are having a final derived form as this. So usually they used to change these values. It might be 20, 19. They used to change them and this least count value used to change. So just understand the stepwise procedure. If they ask you the least count, you can use this general equation. So compared with this, 1 millimeter is going to be my least count in the main scale. Least count in the main scale. And n is going to be the number of divisions coincided with the main scale. Number of divisions in the vernier scale coincided with main scale. Okay, so I think that part is clear. Just get an idea how you find the least count. We are finding this length and this length. We start to equate them. Find the smallest division in the vernier scale, which is this. So you know x is going to be this amount. If we compare both of these segments, we are having a small amount remaining. This will be known as my least count. So in order to find that, we must obtain the difference. Okay. So usually they used to vary the question. Sometimes they used to even break this further, where the division will be 0.5 millimeters. So again, you have to change that. In order to find my least count, 0.5 or whatever division we choose to coincide. Let's try some question in the future. Right. So if we get ready to the part, we'll be having two types of zero errors. One is going to be the positive zero error, and the other one will be my negative zero error. Now you should understand my zero marks at the main scale and the vernier scale. They should every time coincide with each other. Now let's say, now you should understand the diagram of our vernier scale. We'll be having some external jaws and there will be internal jaws as well. And that is my vernier scale and that will be my main scale along here. So somewhat I give direct. So when I bring both of these jars together, the zero marks should coincide. But due to unnecessary usage, sometimes when you bring them together, this 0 mark can go further inside. Sometimes by excessive force, this can go due to some excessive force, this can move some distance inside. So instead of coinciding with the 0 mark, this 0 will be somewhat left to this main scale. The 0 mark in the vernier scale will be somewhat left side to the main scale. So these sort of error are known as zero errors. And there are two types of zero error, which is known as positive zero error, and the other one is negative zero error. So you should understand, when I'm going to obtain a measurement, I should drag it to 0 and then it has to be moved further. So it is something like the measurement is getting smaller, right? If I had some measurements to be measured, I should move only a small distance. If I'm going to obtain a measurement, I'm going to move this way down. So this 0 mark should go through this 0 and then along here. But for someone who is unknown with the zero error, might get the idea that whatever value used to coincide, this is the measurement, like 3. But you should understand, if it was starting from 0, it should have gone a far distance, right? From somewhere on here itself, it used to coincide with 3. So if it was in the 0 mark, it should go further inside, somewhat a value like 5, 6. So there's a reduction in the reading. So in order to correct that, we must add this zero error. We must add this zero error. So these sort of zero error are known as negative zero error. Just we identify these terms. Negative zero error, we used to add them. Okay, negative zero error. Negative zero error. So we must add this value. We must add this value. We must add this value for our measurements. Okay. So first of all, how are you going to find the negative zero error? Just an example. Let's say the 0 mark is somewhere on here, and the 0 mark is somewhat left, which means there's a negative zero error. So we must add this to my final reading. So if I had my main scale and the vernier scale coinciding at somewhat a distance, let's say this is 3 and this is like 5, we should find this length. And also we should find this length. So you should understand, something like our least count, the gap is going to be my zero error. My gap is going to be my zero error. So from this length, we must deduct this length. So let's say the least value is 1 millimeter, and the least value of him is going to be somewhat 0.09 millimeters. So if I obtain the difference, 3 millimeter will be this length. Let's take it as 0.9. So this length is going to be 4.5 millimeters. So the difference is going to be 0.5 millimeter. And this will be my zero error. So see here, this length is 4.5 millimeters. I obtain it by 5 into 0.9. And this is going to be 3 into 1 millimeters. So the difference is going to be 0.5 millimeters. So it has to be 1.5 millimeters. And this will be my zero error. And we must add this to the reading you are going to obtain to find the actual answer. Right? So this is my first case, negative zero error. When the zero mark of the vernier scale is to the left of the main scale, will be resulting with a negative zero error. And we must add this to my final value to obtain a right answer. How you are going to find the negative zero error? See where these used to coincide. So by this least value in the vernier scale and the least value in the main scale, find this length, which is 0.9 into 5, which is 4.5 millimeters, and 1 into 3, which is 3 millimeters. The difference in length will get you the zero error. Okay. And let's get to the part of positive zero error. Let's get to the part of positive zero error. We'll be having, so you should be able to understand that in the case of negative zero error, we had the zero mark to the left of the main scale. But in here, we'll be having the zero mark of the main scale. In the vernier scale, will be somewhere around here, which is to the right. Now, this reason you can actually get an idea. Now, let's say in one of my external jaw, there's a corroded layer, somewhat a thickness. There's a corroded layer. So when I bring my internal jaw close by, it used to get to this point, and you can't move it further. It seems like you have got to the right point. But if you check that, there's an extra measurement, which is the measurement of the corroded layer. So this would result a zero error. It won't come to the exact point. So the zero mark is stuck somewhere to the right. So in that case, there's a positive zero error. Positive zero error. And you must understand, if I'm going to obtain measurement from this instrument, we are having the external jaw. There's a corroded layer. Let's say when you place a metal bolt, you're obtaining an extra distance. Apart from its diameter, you are having an extra distance. So you obtain a greater reading. So we must obtain the difference to find the right answer. So positive zero errors, we must deduct. We must deduct them. In here also the same thing. To find the zero error, check where these used to coincide. Let's say both of them are 3. So you should understand this length is going to be 3, and let's say the division is y. 3y, and let's say the division is x. So this will be 3x. So if I obtain the difference, 3 y minus x. So what is y minus x actually? It will be my least count. So you can clearly substitute it like 0.1 millimeters. So 0.3 millimeter will be my reading. So make sure that you're going to remember this. When you're having different scales, obtain individual measurements and obtain the difference. But when you are having the same scale which is coinciding, like 5 and 5, 3 and 3, just take that number and multiply with its least count. 3 into the least count. So that you are able to find the zero error. And now this technique, it doesn't matter whether it is positive zero error or negative zero error. Right? Only thing you should understand is check whether the zero mark is to the right or to the left of the main scale. If it is to the left, we are having a negative zero error. We must add that reading. And suppose we are having to the right, we must subtract that amount, which means you are having a positive zero error. Okay, so these are the parts just before the usage. You must check whether there is zero error. Even after the reading, it's not a problem, but you must check that. So let's look at how you're going to obtain the measurement using a vernier scale. Now you should understand we are having a zero mark in the main scale and zero mark in the vernier scale. Now when you move this, obviously you have to move it to the right. So this zero mark would be at somewhat a distance. So what you have to do first is from this zero mark, and be careful with the ruler, you might confuse it. This is the edge of the ruler. We are having zero around here. With the zero mark, draw a straight line. It's not a must, but to avoid confusion, just do that. See the value which is just above. See the value just in front of this. That will be my main scale reading. What you have to do? In the zero of my vernier scale, draw a straight line. The scale represented in the main scale. The scale mark in the main scale, just before this line, will be my main scale reading. And see where they used to coincide. There'll be somewhat a distance they used to coincide. So let's say this is 5 and this is somewhat 9. Now, no need to obtain this measurement. Obtain the vernier scale reading and multiply it by the least count. So the equation is reading equal main scale plus vernier scale into my least count. Main scale plus vernier scale into my least count. My main scale is going to be the mark before this line, and my vernier scale is the point where these used to coincide. Where these used to coincide and multiplied by my least count. If you had an example, 0 somewhere at this point, 7, 9, and we are having a 0 mark at here. Let's say 5 used to coincide. The least count of the instrument is 0.1 millimeters. So to obtain the reading, the line before this, just look at the number before it. It is 7 plus 5 into 0.1, which will be 7.5 millimeters. Now, let's say this is in millimeters, okay? Be careful with that scale. If you are having a longer line, it represents the centimeters, okay? So this is the way how you are going to obtain the measurement of a reading. So this is the way how you are going to obtain a measurement using a vernier scale, okay?